So first, I would like to congratulate Claire for her nomination on a professor position in this prestigious institution. Above all, I would like to congratulate her for her numerous contributions to fundamental aspects of mathematics, and to thank her, of course, for the invitation in this conference. So today, I will mostly employ analytic language to consider the extension problem of sections defined in vector bundles on analytic varieties. But in fact, most of what I will say makes sense in pure algebraic geometry, although some of the proofs are unknown in the algebraic context, but most of the statements are particularly interesting in the algebraic situation. So what is the general problem? So you take X to be a complex analytic variety. Which I will assume to be Keller. And either compact or complete Keller. And of course, what I have in mind is mostly the application to projective varieties, characteristic 0, Taylor C, or maybe something like a proper morphism above an affine base, for instance, with projective fibers. And then one takes a line bundle, holomorphic in the analytic category. And of course, things work well only for a joint bundle. So you're considering the twist of L by the canonical bundle of X. Then one takes a subscheme or analytic subvariety, but not necessarily reduced. So it's the zero variety of some ideal. And then, Y, sorry. And then you equip, of course, with the structure sheaf, which is a quotient by these ideals. And then the question is, can one extend sections? Namely, is the morphism, the restriction morphism for the adjoint bundle, so from sections of X to sections of Y, is this surjective? Of course, it looks like an extremely general problem. And in fact, we will see that there is a fairly general good answer, I believe, to this. Maybe not for all subschemes here, but for large number of subschemes. So what we need actually are subschemes defined by multiplier ideal sheaves. Okay, so I have to introduce in the analytic context multiplier ideal sheaves. So in the general analytic context, you take a quasi-plurisobharmonic function on X with analytic singularities. So by this, one means a function such that the complex Hessian is locally bounded from below, say by a Keller form. So you take omega to be a Keller form here, Keller metric. And in the non-compact situation, C would be a continuous function, so it may be unbounded at infinity. One assumes that locally, psi can be written in the form psi of z is a constant times logarithm of a sum of squares of holomorphic functions, where C is positive and the GJs are holomorphic. And then to this function, one associates what I will call I of psi, which is defined to be the sheaf of functions of terms. So this is sheaf of terms at point x, so that there exists a neighborhood of point x on which the integral of f squared with respect to the weight exponential minus psi is convergent in terms of local coordinates. So here I assume x to be non-singular. But actually, most of what I will say is insensitive to singularities. So if you have singularities, because you're considering integrals anyway, you can integrate on the regular part and then extend the sheaves by the L2 condition, and everything will still be true in the singular situation. But to make things simple, I assume x non-singular. You can desingularize otherwise. And so you take the Lebesgue measure in some coordinates. Okay, and then, well, that's the type of sheaves that we allow. Of course, there is a constraint. There is a necessary condition for such a coherent sheaf to be a multiply ideal sheaf. It is always integrally closed. It's easy to see because it depends only on the absolute value and the size of the function. It's always equal to its integral closure. So in the end, you are dealing with integrally closed subsystems. Okay. So now, of course, you can consider multiples of psi. And this can be computed by means of Hironaka desingularization theorem. So in fact, the L2 condition here for the multiple is expressed locally as integral on some neighborhood V of f squared divided. So you replace psi or m psi by this quantity. So you get the sum of gj squared to the m times c. And you want this to be finite. Okay, but then by Hironaka, there exists a modification which can be obtained as a composition of blow-ups such that Well, if you consider the ideal, which is not the multiple ideal, the ideal generated by those functions locally, so you take the functions that define the poles of psi, okay, associated to psi. So if you, well, actually you can take the integral closure, and then if you take the integral closure, it will be globally defined, and the local conditions have to glue, so it will be a global coherent ideal on X, and then you can obtain that the pullback now is an invertible ideal, so it will be x twiddle of minus e, which means that now the singularities here upstairs on x twiddle are equivalent to those of a single holomorphic function. And you can assume that this divisor now is a normal crossing divisor. And say that locally this is sum of mj, ej, and then you have coordinates like w1, wn. Okay, and then you make the change of variable z equal mu of w, and then you get the condition that the integral of f composition with mu of w square. Then you should not forget here the integration measure. So you have the Jacobian formula, and the Jacobian formula will be given also by a normal crossing divisor, and then you have some monomial here, some monomial in the w variable, divided by then some other monomial, which is essentially, well, maybe I denote by alpha the components here, so you will get something like w alpha to the 2mc. And then, well, you see that way that you get a coherent ideal, and that you are going to have jumps for a discrete sequence of exponents exactly when those integers here reach some integral values. Okay, so you will have a discrete sequence of jumps. An infinite one, starting at 0. Such that the multiple ideal sheaf is constant in each of corresponding intervals. And say is equal to np psi for m in the range from np included to np plus 1 excluded. And of course, well, the easiest case is when your subscheme Y is a non-singular hypersurface, reduced non-singular hypersurface. And then, of course, you can find already without blowing up, in that case, that you have holomorphic coordinates that locally y is z1 is 0. Then you can take locally psi to be equivalent to log of z1 square. And then, of course, the jumps are just the integers. So in that case, MP is P, all integers. And then the corresponding ideal sheaf is just the reduced ideal to the power p. Okay, so that's O of OX of minus p times 1. Okay, so now I have all the notation that I need to state the main result. So the assumptions are, so you take X to be a Keller manifold, which is assumed to be either compact or maybe just weakly pseudoconvex. So this will cover, of course, the case of projective algebraic varieties, and this will cover the case of proper morphisms over affine varieties. Weakly pseudoconvex means that there exists an exhaustion function, say rho which is plurisubharmonic and an exhaustion. I will assume it to be smooth, okay, without any strict positivity assumption. And now take L, a line bundle, equipped with a smooth Hermitian metric. H, such that now we need a curvature condition. And the curvature condition will measure how much the line bundle has to be positive in terms of the subvariety Y from which you want to extend. And the condition is that if you take the curvature of LH and you add, so the curvature is here, I put I over 2 pi times dd bar log h minus 1. So it's just a form which is in the first term class of L, okay, as usual. And then you have to take the same thing in terms of the quasi-plurisubharmonic function that defines y. Okay, so you have the function psi that defines y. So maybe I denote it by psi y. Okay, and then you have to multiply by the multiplicity that you want to reach. Okay, so you have to multiply by t, and you take dd bar of this. And then you have to assume that this is semi-positive for all t in the range that goes from the first non-zero jump to the piece jump, and a little bit more. So you have to go a little bit beyond the piece jump for some delta positive. And then the conclusion is that the restriction morphism from the adjoint bundle onto what I will denote by YMP So YMP here is the subscheme, well, in the algebraic context, which is the zero variety of the ideal sheaf associated to the piece jump. And of course, the structure sheaf is defined by this ideal. No. This is, well, this is in the sense of currents. Yeah, this is in the sense of currents. But, okay, so this is important to make the remark.
What was the question? We can't hear.
Yeah.
What was the question?
So the question of Claire was, what is this in the sense of currents? So yes, it is in the sense of currents. It's a positivity here in the sense of currents. You have to deal with currents because psi has singularities, of course, along y. And the positivity is therefore taking the sense of currents. But you assume psi to be smooth outside of y. And the metric h is supposed to be smooth. So in fact, it is enough to have this positivity outside of y. So if you take it outside of y, then it's no longer in the sense of currents. It's just in the sense of positive forms, smooth forms. Okay. And of course, the algebraic geometers might want to have a more algebraic statement because it looks very analytic. Okay. So algebraic counterpart. So this map is surjective, yeah.
Would it do a statement also about the delta?
Delta can be arbitrarily small. You have to have some delta positive in the statement. So you need some delta positive. Maybe, well, I heard that my former student, Junyan Cao, maybe has improved the interval here. Maybe it's enough to have positivity around MP, but this is still not completely written. Okay, so you might improve the interval here. I might prove at least I need the interval from the first jump to the piece jump. So in the algebraic setting, of course, you would take x to be, say, projective or proper over affine. And then what would be the psi in algebraic geometry? So you take, of course, x to be algebraic. And then you would have an auxiliary, say, vector bundle or sheaf over x, and a section of this. And you would take psi of z to be some constant times the log of the Hermitian norm of the square of your section with respect to some Hermitian metric or possibly Finsler metric on the vector bundle. So where HE is a Hermitian or Finsler metric on the vector bundle E. Which you assume to be smooth. And of course, when you have such a function, the dd bar of psi is bounded below by minus the curvature of E, essentially. So the lower bound that you get for the defining function psi is directly related to the positivity of the vector bundle E. The more E is positive, the more negative part you have here in psi. Okay? So the exact formula is that ID bar of psi is bounded by minus the curvature of E applied to section S divided by S square, everything in terms of the metric on E. So it also works in terms of Finsler metrics. And if you have sections of some symmetric powers, of course, you will get only a Finsler metric and not necessarily a Hermitian metric. So it's better to deal with the more general case if you really want to have a completely algebraic statement. So now if you turn back to this condition, this will relate the positivity of L with the positivity of E. What you need is a semi-positivity. So, of course, there is one trouble, that semi-positivity is not really a concept of algebraic geometry. So this is a further remark. So semi-positivity of a line bundle or vector bundle is somehow a poorly understood concept. So it's well known, for instance, that if L is semi-positive, then this implies that L is numerically effective in the sense that for every curve, the degree on a curve is non-negative, but the converse is wrong. On the other hand, you have a slightly stronger algebraic property, which is, for instance, that L is like the tensor product of two line bundles, say, where G has some multiple which is generated by sections. So some multiple is generated. And H is flat, namely it's in pick 0 of your variety. So now this is perfectly defined in algebraic geometry, but unfortunately this is a bit too strong. So this implies that L is semi-positive. But there are definitely nice examples of semi-positive bundles which are not of that type. So it's still a little bit of mystery what is the exact meaning of this condition in analytic geometry. But anyway, you have close concepts. Okay. So now I'm going to enter into details of the proof. Some further results. So in the analytic context, it is very important that this theorem comes with precise L2 estimates. So this comes with L2 estimates. And the L2 estimates may have algebraic applications. For instance, one recall a very important application. So precisely in the non-projective case and the non-compact case, so you take a proper family over a base. So you assume S to be irreducible. And you take a projective morphism. And assume the fibers are non-singular. And now you look at the plurigenera. Namely, they number of independent pluricanonical sections on each fiber. For any given multiple m. And then the conclusion that this number is independent of T. And the result was first proved by Yung-Tong Hsu, 1997, using precisely some form of the extension theorem. And this was first in the case where xt is of general type for every t. In that case, you have strict positivity somehow, so you can use strict positivity. It's a little bit easier. But then Yung-Tong Hsu came a bit later, around 2001 maybe, with a general case. So you have no assumption, general family of non-singular projective varieties, and it works. And the proof was improved further by Mihai Paun around 2004 with a very, very simple proof. But it turns out that the proof uses in a crucial way the L2 estimate. Explicitly, it uses the uniformity of these estimates when the powers m go to infinity. And I don't think there is any algebraic proof at this point of this result, even characteristic 0. So it's, I would say, a challenge to algebraic geometry, to pure algebraic geometry, to have a purely algebraic proof for non-general type varieties. Kawamata here, the first proof of Hsu was translated into algebraic language by Kawamata. So actually the proof was almost algebraic, and Kawamata made it purely. Then, unfortunately, the problem of invariance of plurigenera in the Keller context is not yet solved. So one of my hopes is that the general version I've given of the extension theorem, which of course holds true without any projectivity assumption, might imply this. But still, even in the proof by Paun, although you don't need the canonical to be strictly positive, you need the existence of some auxiliary line bundle to be positive. So the Paun's proof still uses the existence of an ample line bundle. But I have hopes that maybe I have at least some possible strategies for the general case, but I didn't succeed at this time. I believe that Yung-Tong Hsu tried a lot also, but it's still an open problem. So this is open in the Keller context. So since I discussed strict positivity, of course, I should mention that the main result is very trivial if you assume strict positivity. So that's a remark. You have the Nadel vanishing theorem. Which, of course, in the algebraic context is just a Kawamata-Fivek. Which tells you that if you have a line bundle and a singular emission metric, so you take H now, but H now is allowed to have singularities, okay? So maybe it's something smooth, multiplied by a weight, but the weight now can have singularities, can have poles, so it's a singular plurisymbolic function, or quasi-plurisymbolic function. And you assume that this singular metric on L now is strictly positive. So it means that in the sense of currents, it is bounded below by a positive multiple of the Kähler form. Then you can prove by L2 estimates that all cohomology groups of the adjoint bundle, but you have to twist by the L2 condition, and the L2 condition introduces the multiple ideal sheaf of your correcting factor exponential minus phi. And this will be 0 for all q at least 1. And now if you apply the Nadel vanishing theorem to my situation of the extension problem, now the condition, so a stronger curvature condition for the extension problem would be that if you take the curvature of LH, but now H is smooth. Now you have a smooth metric on LH, but then you correct with this psi, which defines a subvariety Y. And then you take exactly NP times I over 2 pi dd bar psi. But now instead of allowing a small range, you assume strict positivity here. So you assume this. Then, of course, you can equip with the new singular metric, which is just h multiplied by exponential minus mp psi. And then the corresponding multiple ideal sheaf will be exactly, if you take that weight, the corresponding multiple ideal sheaf is I of mph. And of course, you get that all cohomology groups here vanish. And especially, you can consider the exact sequence which defines the structure sheaf of the subscheme. So you take this obvious exact sequence and you twist it. You twist the exact sequence by the sections of Kx tensor L. And then you apply the long exact sequence of cohomology, and then you will get the morphism from sections on X to sections on the subscheme will be surjective simply because you have killed the full H1. But of course, this is somehow a drastic assumption. You assume strict positivity, and the strict positivity implies already that your manifold is essentially projective, because you have some bundle with strict positivity in the compact case. Also, if you want to have applications, say, to the minimal model program or the abundance conjecture or to the asymptotic analysis of linear systems, you want to get rid of this strict positivity. So you absolutely want to have an extension theorem with a much weaker assumption where you don't put strict positivity here, but only weak semi-positivity. And this is the main goal of the general theorem, that you still have surjectivity without killing the H1. Of course, in my theorem, you don't know anything about the vanishing of H1 or HQ. You only prove surjectivity without being able to say anything about the H1. And most certainly H1, you can give examples where H1 will not be 0. A very simple example is in the case of a proper morphism. So if you take the fibers, so you want to extend things from the fibers. So this will be your subvariety, okay? So it's contained in the total family. And the psi here, if you have the parameter t here, you take psi of t to be log of t squared. And of course, here, because you are on the disk, the IDD bar of psi is essentially semi-positive. It's just a direct measure at 0. So you have absolutely no condition on the line bundle. It can be just, for instance, an element in peak 0. And then this element in peak 0, if you have, for instance, abelian fibers, will have H1 cohomology, but still you can extend. So this is an example of non-vanishing of H1 or HQ in that case. Okay, so now I have some time to discuss the ideas involved in the proof. And so one important concept is the concept of residue measure. Associated with psi. So the observation is, that's an easy one, that if you take the first jump, M1, okay, then if you look at the multiple ideal sheaf, by definition of M1, this is everything. This is everything for M less than M1. And then it is non-trivial when you reach that value. Okay, it's different from OX for M at least M1. But then it means that in the L2 condition, of course, F will vanish, but very little, because if you are just over M1, below it's convergent, so the ideal sheaf will be reduced. So if you take the first jump, it is automatically reduced. In fact, analytically, it's just Hölder inequality. So Hölder inequality implies that the first scheme here is reduced. So square root of I of M1 psi is I of M1 psi. And now in this context, there is a natural procedure which was introduced by Ozawa. I should have said earlier that the first important extension theorem in the L2 context was obtained by Ozawa Takegoshi. So Ozawa has, I think, at least 6 or 7 papers along the years. The first one was 1987. And then in a later paper, he introduced what I call the residue measure. I don't think he introduces that way. So you consider the first jump. Now you have the YM1, which is the 0 variety of your ideal sheaf here. Of course, the situation is extremely general. I don't claim at all that the support is the same for all multiples. You can, of course, have lower and lower multiplicities, and you can gradually increase the number of components of your schemes. The scheme can be reducible. You may have as many components as you want. It's extremely general. But here we take the first value, and then this one is reduced. Okay. Now I'm going to define a measure which is supported on, say, the regular points, which somehow depends on the ambient kilometric, but not too much, but depends in an essential way on the singularities of your defining function. So if you are in the algebraic context, again, psi in the algebraic situation would be defined by the log of a section of some auxiliary line bundle. And then what you need to consider is the singularities of the zeros of your components. So you look at the ideal sheaf generated by the components of your section, where R, say, is the rank of the bundle E. And then you are going to define some sort of discriminant measure attached to the coherent ideal here. So again, it's an analytic concept, but I believe it has potential meaning in algebraic geometry as well. So what's the analytic definition? You take here the tube, which will look like this. So you consider the tube of points z in x such that t is less than psi of z is less than t plus 1. And of course, y is essentially contained the zeros of your section, so it corresponds to the poles. Okay, so y is certainly contained in the poles of psi, minus infinity poles. And now you're looking at the tube corresponding to t here, t very negative, t going to minus infinity. Okay, so you look at that tube. And now, well, you want to define a measure. So to define a measure, you take a compactly supported continuous function on y m1. So it's a continuous function with compact support. The singular set, of course, this may be singular, but the singular set would be negligible. So you could take it in the regular part. Well, it doesn't matter much. This is unrelated. This is a different, of course, this ideal sheaf is a little bit related to the multiple ideal sheaf, but it's distinct. Okay? The multiple ideal sheaf is the sheaf of functions such that, well, in this situation, such that the integral of f squared maybe you can take some constant here, okay? M1C converges. So you have some relation between this ideal sheaf and the multiple ideal sheaf, but they are definitely distinct objects. Sorry? No, this is an example. Okay. Because I don't want to, I know the audience is composed mostly of algebraic geometers, so I want to give examples where these concepts make sense in algebraic geometry. So this is just a situation that you can compute in algebraic terms. Okay, so you would take such a function here.
But the construction of the residue measure works for every
with analytic singularities. It might be that this concept makes sense in a very general sense without any assumption on the analytic singularities. And by the way, it has been proved recently by Guan and Zhou that the jumps, anyway, make a discrete sequence, whatever are the singularities. So even if you are in complex dynamics, because I guess in complex dynamics you may have such functions which occur in a natural way, then you still have this discrete sequence of jumps without any assumption. You can have fractal singularities and it still works. It might be that this measure is still defined without any assumption, but this is a non-trivial analytic problem. It might be interesting in complex dynamics. So what is the definition of the measure? Okay, so you have this compactly supported function here. So you take an arbitrary extension to x. Okay, here you are in the ambient variety x. So you extend it as a compactly supported function on x. Okay, and now the measure is a linear form on continuous functions. And so you are taking actually the limit as t goes to minus infinity of the integral on the tube of the extension multiplied by exponential minus m1 psi of z. And here you have to multiply with the Kähler volume on x. Okay, so you take the Kähler volume on x, so it's just simply 1 over n factorial omega to the n, where n is a complex dimension. And then here m1 is just the critical exponent of convergence. So if you would integrate not on the tube, on the hollow tube, but you would integrate on the full tube, the integral would be divergent. But if you turn this by Hironaka and you go to polar coordinates, you are going to integrate something. So you are in polar coordinates, and the critical exponent will be just 1, so you have R2 in the denominator, and then you integrate on something, the radius is between exponential t and exponential t plus 1. But then you have, you integrate the logarithm between exponential t and exponential t plus 1, and then the log, of course, has integral 1. So when you integrate on the tube, then the integral is convergent, and doesn't care about the choice of the extension. It takes only the value that is the limit on ym1. Because if you have a function that vanishes, of course it will become small near y, and when you approach y, this will converge to 0. Okay, so this is a perfectly defined measure. Of course, it's hard to compute because you need to know what is the Hironaka sequence of blow-ups. But anyway, it will be a perfectly defined metric. 4. And then, of course, it doesn't depend too much on omega, because locally, if you take two different Kähler metrics, they will be comparable by constants. So it's... And anyway, the theorem doesn't depend at all on the Kähler metric, because you are dealing with n0 forms. So, in fact, there is the observation, which looks strange. That if you integrate, okay, so you have a section of kx tensor L. So, of course, kx tensor L is the same as lambda n t star x tensor L. So to integrate the form, you have to compute the norm with respect to the Kähler metric here and the Hermitian metric here. So the norm of your forms depends on omega and h. And then you remultiply here by the Kähler volume, but it just turns out that these things cancel. Because when you increase the Kähler form, you increase the volume, but then you decrease the norm by the same factor. So actually, this product is independent of the Kähler form. So it's a bit surprising that you need the Kähler assumption, but in the end, the L2 estimate is completely independent of your choice of Hermitian metric. And in the same way, the residue measure will, in the end, not depend on, in some sense, on the integrals will not depend on the choice of the Kähler metric. So it's absolutely intrinsic. Okay. So, sorry? But the Kähler assumption is crucially needed in the proof. Okay, so now the claim is that well, if you are given a section on the subscheme, then there exists an extension. There exists a capital F, which is on X, such that the L2 norm well, you have to correct by a strange function, which is essentially well, 1 over 1 plus psi square times exponential minus m1 psi times dvx omega is less than a constant, which is 34. Well, this is just technological. I mean, it can be improved over delta. Delta is a delta occurring in the assumption times the integral over y, m1, with respect to the residue measure. Okay, so you integrate your section F here with your matrix, and now you plug this thing well, in that case, in the algebraic case, it looks like a Jacobian. So it's given by some square of a determinant. It can be computed explicitly in the algebraic situation. And there are even people who obtain the optimal constant here. However, there is one difficulty, and that occurs already in the divisorial case. So by Hironaka, you can reduce to the case of normal crossing divisor. So suppose your y has a number of components. Okay, and then you compute the residue measure. And it turns out that the residue measure blows up in the intersection. So problem, this measure here on the first, these are components, not the values, okay? So maybe I didn't like this. Okay. So on the first thing, yeah, this blows up. Namely, it's not a finite volume on the mutual intersections of the components, even in the divisorial case. Which means that this is not sufficient to prove the main theorem I've given, because if you have a section on the union, it might not be zero. It might not be zero here on the intersection. And then if it is not zero on the intersection, this integral will be divergent. However, the qualitative statement still holds true. So I have very little time to explain that. So in that case, in the complicated case, in the arbitrary case, we essentially lose track of the L2 estimate. But the qualitative statement is still true. So the proof relies... It's the extension. Okay, you have the surjectivity, so, well, it's implicit in my notation. So you extend with bounds, but the problem is that with respect to the only natural measure that you have, unfortunately, for some sections that you want to extend, this is divergent, so you lose the L2 estimate. Nevertheless, the qualitative statement is still true. The proof relies on approximate solutions, on approximate Bochner-Kodaira formula, which I think is a new idea. Well, I used it already in some circumstances, but in this context it's a bit new. Then from this, you don't solve exactly D bar. So of course, what you have to do is to extend locally a smooth functions, and then you use cutoff functions, and then you solve D bar, and you apply Hormander's L2 estimate, and then you solve some equation, but then you will have an error. So W epsilon will be an error term. And you have an estimate like this. The integral of f of the solution plus 1 over, so this is the error. And the error here has coefficient 1 over epsilon. Maybe capital F. Okay. That's it. And then you have the integral on ym1 with the residue measure. Okay. Okay. You want to extend something. Okay. With the residue measure here. All this depends on some parameter epsilon. And so this thing blows up, unfortunately. So this term goes to infinity. But you can show, and this is the important idea, that if you analyze very precisely the Bochner-Kodaira formula, it blows up, but in a smaller way than the coefficient 1 over epsilon. So it blows up at a speed which is less than 1 over epsilon. And therefore, you completely lose control on the solution, but you don't lose control on the error term. So you can still prove that because of this good coefficient 1 over epsilon, then the error term will go to 0. And then you prove that the co-boundaries are dense in the cocycles. But then if you are in a compact manifold, especially in a productive case, you know the cohomology is finite dimensional, and therefore it is Hausdorff. And if the co-boundaries are dense in the cocycles, because the cohomology is Hausdorff, then it has to be 0. And therefore, you still get the qualitative statement, but you lose the precise estimate on the solution. So now I have already over time. So what are the left open problems? The left open problems would be to have good L2 estimates in the general setting. This is unknown. In fact, I also have L2 estimates for the non-reduced situation, but I am in trouble when I have several components meeting. So I completely lose control of the solution on the singular part of the subscheme. So I believe it would be important to have a suitable L2 estimates that is true in general. My guess is that such an estimate could exist. And maybe it will have important applications to general problems of algebraic geometry like abundance or the MMP, where you constantly use induction on dimension. For the MMP, for instance, you proceed by induction on dimension, and of course you need extension theorems. So but that's still the future, I would say, so I will stop here.